Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is Gibbs function and chemical equilibrium, and the section in the textbook is 16.1. Here are the learning outcomes. At the end of this, you will know what the Gibbs function represents regarding chemical equilibrium. You'll know the difference between reaction equilibrium and reaction kinetics. You'll understand where the chemical equilibrium relation originates, and this is the relationship that I'm talking about. And you'll be able to quantify delta G, which is the change in the Gibbs function, as a function of the chemical reaction progress. So what I want to do is I want to introduce the Gibbs function and make you understand why it's important. So let's go ahead and look at this box I have over here. This is a picture from the textbook where we have CO2 molecules, CO molecules, and O2 molecules. And we have a mixture of them. And the question we want to ask is, why do we have the particular ratio of those molecules that we do? For example, why don't these two COs right over here get together and form a CO2 molecule? Or why doesn't this CO2 molecule go ahead and dissociate and form a CO and an O2? Why do we have the particular composition that we do? And that's called the chemical equilibrium composition that we have. So we're going to be able to answer that, and we're going to be able to answer it using thermodynamics. So first of all, let's go ahead and look at this system right over here. And let's write down the first law energy balance for it. And so imagine we have some small amount of heat, del Q. It might do some work. We'll have the system doing work, so I'll do minus del W. And that right there would be equal to the change in internal energy of my system. And so if the amount of work it is doing is just reversible work or PV work, so you can imagine this is actually maybe better to draw this as a piston cylinder device. So if heat was to go in or out, the system could go up and down. And also, as the reactions occur, it could go back and forth. We could go ahead and write this instead as del Q, and this would be minus P dV is equal to du. So differential change in the internal energy. So that right there, that's the first law of thermodynamics. Now let's go ahead and write down the second law of thermodynamics. And the second law of thermodynamics said that ds, which is our change in entropy, a differential change in entropy, we know has to be greater than or equal to the amount of heat normalized by temperature. So if the differential amount of heat is not going to be a change in temperature, that gives us a differential change in the entropy. And that right there, that is the second law of thermodynamics. So we know that both of these conditions need to be met for any system to exist. And so what I'm going to do now is I'm going to go back to the first one. I'm going to go ahead and substitute in del Q right in over for that del Q right there. So I'm essentially going to combine these two relations. And then I'll collect everything on one side. So what this ends up saying is du plus P dV minus T ds is less than or equal to 0. And so what this is a combined first law and second law together. And it's also nice because I've now written this all in terms of properties or differentials, and so I don't have any path-dependent functions like heat and work. So we're going to hold on to that equation for right now, and let's go ahead and we're going to do something else in parallel. So I'm going to go ahead and introduce or remind you of the Gibbs function, which is G, and we saw this once before in chapter 12. G is defined as H minus Ts, which is the enthalpy minus the temperature times the temperature. Times the entropy. And so now what it's going to do is I'm just going to do some calculus on this. I'm going to look at what a differential change in the Gibbs energy is. And so we're just doing calculus. So dG is going to be equal to dH, and then I'm going to distribute the differential between Ts. So minus T ds minus S dt. So right there, that's just some calculus on that definition of that function. Now, also remember, we know what enthalpy is defined as. Enthalpy is defined as U plus PV, and so I'm going to go ahead and substitute in the differential form for dH, doing a similar thing with this U plus PV. So this is now going to end up being equal to, so I'm taking that term right there, this becomes du plus P dV plus V dP, right? Okay, so that's the dH term, and then minus T ds minus S dt. So that right there is a differential change in the Gibbs energy. And now we'll go ahead and we'll make one other assumption. We'll assume we're going to look at what changes in G is at a constant temperature and pressure, which means we're not going to let temperature or pressure change. So what that's going to do is that's going to mean that term right there is going to be equal to 0, and that term right there is going to be equal to 0. So now if I see what I've got left, I have du plus P dV minus T ds, right? And so that is what dg is at a constant temperature and pressure. Now look at this and go back to that equation that we looked, which was the first law. This is just calculus in the bottom. Up here is the combined first and second law. And what that tells us is that in order to satisfy the first and second law, we know what we just derived has to be less than or equal to 0. And this gives us this sort of very, very useful, simple equation which says that the Gibbs function, any change in the Gibbs function, has to be less than or equal to 0 in order to satisfy the first and the second law. All right, so let's look at this a little bit more, just kind of qualitatively. Back to our system that we had, and we just said that dg has to be less than or equal to 0. So let's go ahead and do some thought problems. So we've got our box, and the question we're trying to answer is, why do we have the particular composition of CO, O2, and CO2 in this box that we do? Right? So let's go ahead and imagine that over on the, we're going to draw this, what I'll call reaction diagram. Over on the far left, let's imagine this is a box full of just CO2 molecules, and then this over here represents a box of just CO molecules and O2, and so everything in between, give me numbers in between. So if I go a little bit from the left, that means I'm going to pull apart one CO2 molecule, a little more, I'm going to pull apart two, etc. So I have all CO2 on the left, all CO2 on the right, and everything in the middle is some mixture of it. And so what I could do with this is every time I could go ahead and calculate what is the Gibbs function of inside this box, because G is just equal to H minus Ts, and those are properties. I can find the enthalpy of the box, temperature of the box, the entropy of the box, and I can go ahead and find out what the Gibbs function is, and then I'm just going to go ahead and do it for different compositions. And so let's go ahead and do it and say I measured it at these various compositions, and if I did all those calculations, it would end up with something that might look like this, which more or less says that here's what my Gibbs function is of my box as a function of the composition. And what you'll find, and this is true for everything, is that there's going to be some minimum value. And so dg, well, that's the slope of this line, and dg less than or 0 says for something to occur, for a reaction to be spontaneous, it has to go in the direction of dg getting smaller. Otherwise, it's violating the combined first and second law. So if I have all CO2 molecules, it's going to want to go this direction, there. And if I had all CO and O2 molecules, it's going to go to this direction, and there's going to be the happy medium. This right there is chemical equilibrium, as determined by thermodynamics. All right? Now let me just mention something. This doesn't say anything about the speed with which it happens. And so I can easily have a box of all carbon monoxide and O2, and if I don't provide a spark, I actually am not going to go to this equilibrium composition. I need to get over that activation energy. So we're not saying anything about reaction kinetics, the speed at which something happens. All we're saying is that when eventually, in infinite time or given a little push, all systems are going to go to that equilibrium function. All right. Okay. So let's go ahead and determine an equilibrium relation, more of an equation that's going to go ahead and tell us what that is. All right. So let's go ahead and we're going to look at this generic reaction where I've got some A and some B that are going to go to C and some D. So those can represent any type of molecules we want. And the relation we're deriving is going to be general. So it would be the same with maybe A going to a CD or just a B going to a CD, etc. So there's my equation. Now, if this equation was to go forward, as I've drawn it in this direction, I would have some number of moles of A and some number of moles of B combining, right? Because imagine that reaction that I looked at, I had like, say, CO plus 1/2 O2 going to CO2. Right there, my number of moles are 1, a 1/2, and a 1. So this is kind of just, these ends represent the number of moles that would go forward in that reaction. All right, so here's my equilibrium relation, which said that the change in the Gibbs function has to be equal to 0. And so if I want to find the total change in Gibbs function, I'm just going to add it up over all the constituents that I have. So I'm going to be summing over I, where I is each one of the components, maybe these 4 components here. And I could go ahead and express my extensive G value as an intensive G value. So I have it written here, and I'll write it per mole times the change in the number of moles that I have, right? So this is a intensive property, and that right there is the change in the number of moles that occur. And if I was to add up all of those for all my components, the equation I show here, I have 4, we know that that's going to equal 0 at chemical equilibrium, at the bottom of that curve that I have. Okay? So if I wanted to know what are essentially these change in the number of moles, dn sub I for A, B, and C, well, if I balanced my equation, it's just the stoichiometric coefficients, which the book uses as a Greek letter nu. So for example, the equation I have up here in the upper right, my nu values are 1, 1/2, and then 1 right over there. And so what I could do is I could go ahead and determine what each of those are. And so for example, dn sub A, let's say that this reaction goes forward some infinitesimal amount, some small amount epsilon. The change in the number of moles of A is A gets consumed, it's a reaction, it's a reactant, so it would be minus epsilon, the amount that it goes forward, times nu sub A. I want to know how much C changes, dn sub C. That's going to be positive because it's a product, so it's going to be equal to positive epsilon nu sub C. And I could write that for all 4 of those components and then add them together. So what I end up with is my equilibrium relation that I have here, where I have my Gibbs energy, my intensive Gibbs energy, and just recall G, it's simple, it's just H minus TS. Now I've written in an intensive form, so I'm using the lowercase letters, and we could do those all on a mole basis, times the stoichiometric coefficients of my balanced equation. And if I add up all 4 of those are going to end up being equal to 0 at chemical equilibrium. So right there is my equation that determines where the middle of that curve is, where the minimum is, what is chemical equilibrium. All right, so let's try to do this, what I call an illustrative example. We'll put a little bit of numbers in here, but we won't quite solve the whole thing. Okay, so we'll bring this, instead of reading the generic A, B's, and C's, let's look at something we've looked at before, which is a combustion reaction. So what I have here is ethane. Ethane reacting with air to form carbon dioxide and water. So I've got complete combustion. Right? And so if I want to determine, for example, where would be the intermediate composition of that I have. So if I had some box and I had a bunch of ethanes and airs in it, at what point would it be at equilibrium with the number of reactants and number of products that I have? So what I do to write this, I'm going to call my ethanes E. I'm going to call my oxygens O. And in this reaction, notice nitrogen doesn't participate in the reaction. All the nitrogen goes in, that goes out. So let's just go ahead and neglect this because it doesn't appear in the reaction kinetics that I have. This is the number of N's that I start with is the number of N's that I change with. So dN of N2 is always going to be equal to 0, so it's not going to appear. So we have E's and O's reacting to form carbon dioxides and waters. I'm just going to use shorthand notation. I'm going to think of those E's and O's reacting to form C's and W's. And if I look at my balanced reaction, so if I had a whole box of it, what I know is that I have to take 2 E's, right? Take 2 E's and 7 O's. So let's give myself 7 O's. Like I multiply the whole thing by 2 here. If I take 2 molecules of that, think of just individual molecules, I'm going to go ahead and add it to that. I'm going to go ahead and give myself 2 carbons, 2 CO2s, and then I'm going to go ahead and actually I'm going to give myself 4 of those, and multiply it by 2, and I'm going to give my 6 waters. 1, 2, 3, 4, 5, 6, right? So that's what's going to happen. So what nature is going to do is it's going to take 2 E's, 7 O's, form some of these, and then go ahead and look at that equilibrium relation and say, hey, am I now at a minimum, or should I go ahead and go forward? Should I go forward? In fact, it's also constantly saying, should I go backwards? So it's more or less just bouncing back and forth to try to go ahead and find what that minimum value is. Right? All right, so if I wanted to know, for example, what is dN of the ethane, dN sub E? Well, that is, it's getting consumed, so it's minus 2 molecules. We call it MLC, so it's minus 2 molecules. I want the number of moles. I'm going to divide that by Avogadro's number, 6.022 times 10 to the 23rd. And that would be about minus 3.3 times 10 to the minus 24 moles. Right? So there's dN sub E that would go into my equation. For example, how many carbons do I have, right? So if we go ahead and say, what is dN of the carbon dioxides? Well, that's going to be a positive value. It's going to end up being 4 over Avogadro's number. So I got 4 molecules over Avogadro's number. That's going to give me a positive 6.6 times 10 to the minus 24 moles. And so I can determine all of my dN values. Remember, notice I'm just using my stoichiometric coefficients. And then what I want to do is I want to stick it into my equilibrium relation. Well, my equilibrium relation said that the summation of G sub I e n sub I is equal to 0. I just found all my dn sub i's. And what I need to do now is determine what's my Gibbs function for each component. Well, we know that G is equal to H minus Ts. Now this is of each component, so each one's going to have a different enthalpy and entropy. Temperatures are all going to go ahead and be the same. So here's my box. Right? We have lots of ethanes and waters and carbon dioxides and oxygens in there, and they're constantly bouncing back and forth in this reaction to go ahead and find a minimum. So imagine that here's my box, and I'm going to go ahead and insulate it so that it's an adiabatic, and I want to find out what the equilibrium is. I'm just going to let it bounce around adiabatically until it reaches equilibrium, until it reaches the bottom. So by first law, well, you know delta E, the change in energy, is going to be Q minus W. And if this is a reversible system, so we'll go ahead and let it expand and contract to go ahead and keep a constant pressure on there. We could write this as delta H is equal to Q. So just move the boundary work over here. This is all equal to delta U. And then if it's adiabatic, we know that that is equal to 0. So this is happening adiabatically. There's not going to be a change in enthalpy of the whole system. Like we saw this with adiabatic flame temperatures. We said the enthalpy of the reactants is the same as the enthalpy of the products. Now, the change in Gibbs energy, delta G of the whole system, can be delta H of the whole system minus T delta S of the whole system. And we just said that right there is equal to 0. So what ends up happening is any change in delta G, which we know is going to be negative if it actually happens, if the reaction goes forward, we're going to be concerned with this minus T delta S term. So let's kind of look a little bit closer at what that means. And remember, this temperature is absolute temperature, so it's always going to be positive. So what we care about is delta S. And if delta G is going to be less than 0, what we see is that delta S has to go up. So let's kind of look a little closer at why we know delta S has to go up. Right? So what is delta S of the whole system? Well, we've got an ideal gas mixture. We just simply go ahead and add each one of the components that I have for the amount that is reacting. So we just on the previous found, like what dN and dO and dC is, these values over here on the left-hand side, okay, these were minus because they were getting consumed. So this is a negative contribution to the overall delta S. The dN of C and W, because they're being formed or products, those are going to be a positive contribution. So this is going down, this is going up. My question is what's happening to delta S, and the argument I'm making is that it clearly must be going up in order for the reaction to be going forward. Delta S has to increase so that delta G is going to go ahead and decrease. Okay? Now, one of the things is that if I have an exothermic reaction, okay, I just consumed this at a relatively lower temperature, formed these at a relatively higher temperature. Okay? So these entropies I would expect to go up a little bit because of the temperature contribution of entropy. I'm just forming molecules that are clearly bouncing around faster than the ones that I consumed. So I'd expect those entropies to go up, and they do by the temperature contribution. There's another contribution too, which is the pressure contribution. Right there's the temperature contribution, and we know that that tends to go up for all of these that we are producing. But another thing that's sort of interesting happens is I've got this pressure contribution. Remember, when we have gas mixtures, we've got to use the partial pressure. So as this term right over here, I have the mole fraction Y sub I, pressure of the mixture over P naught. And so here's my mole fraction of Y sub I. Now, when the reaction first happens, so the very first ethane that burns to form the very first CO2 in water, the partial pressures, or the mole fractions of the carbon dioxides of the waters, is going to be really small. This number is going to be really small, so I'm going to be taking the log of a number that is really small. That's going to be very negative. You can check that, right? If you take the natural log of -1, of let's say 1 to the -24, you find out that number is going to be very, very negative, and I've got a subtracting of a negative value. That means that's going to be positive, which means this value is going to be very, very large. So not only is this part really large, this part right over here is really large, which tells me that my entropy per mole is very, very big when the reaction first happens. Now, I'm only multiplying by a small amount each time, but it's still a very large value. Also notice, as the reaction goes forward, the mole fraction increases, this contribution tends to get a little bit smaller, and at some point, I'm going to reach that equilibrium point, and I'm not actually going to burn the very, very last ethane molecule with the last oxygen molecule. Because what I would be doing, effectively, is forming a two-ordered of a state, and then the entropy would begin to decrease instead of increase, and my delta G would no longer be 0. So let's go ahead and look at another interesting thing, which is endothermic reactions. We just saw why exothermic reactions tend to go forward because, well, that heat that they give off causes the molecules to bounce around a lot faster, and so the temperature contribution goes up. But if the temperature contribution goes down, why would a reaction happen spontaneously? Why would it happen at all? And so here's a classic one. And this is, you've probably seen these chemical cold packs before, where you go ahead and you break a little bag inside the bag here and the thing gets cold. And so that's an endothermic reaction, meaning it consumes energy. As it goes forward, it gets colder. And why does that happen? And what happens is, this is what's inside these cold packs. This right over here is barium hydroxide. And barium hydroxide is an incredibly ordered molecule. It's very large too. So this green is the barium, and then these are a bunch of water molecules that are bonded to it. And the whole thing forms a crystalline form, which I show here, the picture off Wikipedia. It's very, very ordered. So the reactant for this is very ordered. It looks like this powder that I show here. And so what is in these cold packs is, here's my barium hydroxide, and it's hydrated with these 8 water molecules, and that's what's being shown in red there. Those are my 8 water molecules. And you react it with ammonia nitrates. That's also mixed in with this. And that's why you have to break the pack. You have to mix these two things together. So that is the reaction that happens. And so what I end up forming is barium nitrate, some ammonia, forming a whole lot of free water molecules. And it's endothermic. It consumes energy. So it absorbs heat, and the temperature is going to go down. So why would this occur spontaneously if it's getting colder? Because that would be decreasing the entropy contribution. Well, look what I have. You effectively have like one molecule over here. This is all ordered. This is effectively one molecule and 2 molecules. Taking 3 molecules, and I'm forming 10, 11, 12, 13 molecules. And I'm going to something that's much more disordered. So although the products are bouncing around slower, it is so disordered, delta S still goes up. It still increases because the disorder contribution is so high, even though the temperature contribution has gone down. The net increase in entropy increases. And so I kind of think of this as like a house of cards kind of idea, in that here you have something that's very, very organized, and all you do is kind of pull one card, the thing just kind of collapses. And that's what happens here. Because I'm getting something that's more disordered, it happens spontaneously. So hopefully kind of gives you just an illustrative example of why both endothermic and exothermic reactions will go forward, are somewhat spontaneous, but they have some equilibrium composition.